Welcome to our 8:30 media Q&A, the future of the world's groundwater resources. Our speakers today are Inge de Graaf from the Colorado School of Mines and Marc Bierkins at Utrecht University. And there is a press release that I will also hand out to go along with this media Q&A.
Okay.
Well, good morning, everybody. Thanks for coming and thanks for the interest in my research. I prepared just a few slides for you just to highlight two of the main results of the poster that I will present later this afternoon. And Marc Bierkins, he's my former PhD advisor, so that's why he's here. So the main question of this research was where and when will we reach the limits to global groundwater consumption? And so the question is, why are we interested in this? So groundwater is the largest available freshwater resource around the world. So for regions where freshwater is not freely available, groundwater is often abstracted. And already we see that many aquifers around the world are depleted. That means that more water is abstracted than it is renewed by the infiltration of the rain. And we already also see that negative effects are occurring in different places around the world. I will mention the negative effects in the next slide. And if you look at of what we will see in the future, we will see that water demands will increase, and due to climate change, freshwater availability will decrease. So we expect that the problems we will experience due to groundwater abstraction will increase too. So this is the first result of the model that I was running. And it shows you the current regions where we experience groundwater depletion. And we can make some zooms for the hotspot areas around the world. And maybe you see already that these are the areas with large irrigation. Large irrigation regions. So these are the areas where we experience a lot of depletion. So what is a consequence of groundwater depletion? Well, the direct result of it is lowering of water tables. And when water tables decline, it means that pumping costs will increase. There are some pictures. Pumping costs will increase, and also it will cost more money to maintain the wells. And another effect is the reduction of discharge to the rivers. So it means that eventually rivers will run dry. And another result is that due to the groundwater abstraction, so the soil will start to compact. And so we call it land subsidence, and that is increasing flood risks. So back to the main question. So what was my main goal of this research was to predict where and when wells will run dry. So I was interested in the question, when will be the moment that a local farmer cannot abstract the water anymore? And as a rule, I used that this is going to happen when the water in the well drops more than 100 meters for 2 years in a row. And this is the map that I got after running the model for a longer period. So from 1960 to 2100. And so this map is showing you for which areas we will experience the limit in the near future. And again, we can make some zooms. So look at the Central Valley. We see that in the south of the Central Valley, we will reach the limits in the near future. And in the middle, it will take a little bit longer, but there's also a problem. The same we see for India, so we see a large area where we will reach the limits in the near future. And also if we zoom to Europe, we see some new areas developing where in the near future the limits will be experienced. So just to wrap it up, a conclusion. So this study we did provides new insights about the sustainability and the resilience of groundwater resource. And this is valuable information for water managers at all levels. And just a final remark, because this is a huge modeling study, and the only thing I want to say about it is, so this study is the first one that uses lateral groundwater flow and groundwater surface water interactions. And by doing that, it gives more realistic results than the other studies around. Well, and with that, I want to thank you for your attention, and we're ready for your questions.
Yeah, are there any reporters in the room who have questions? Please raise your hand and state your name and affiliation. Okay.
It's Henry Fountain at the New York Times. Does the study take into account efforts being conducted or undertaken in California to conserve groundwater?
You mean if you look specifically for the Central Valley?
Yeah.
No, we don't.
Were there any other questions in the room?
Hi, I'm Tim Olson with Earth Magazine. I was just wondering if you could talk a little bit more about the, I guess the input, the data that you used. I wasn't sure if you were including GRACE data or local, any kind of local data, or I know it's obviously a global scale study, so I don't know if you're using like individual well measurements at all or something like that.
Yeah, sure. So one of the main inputs, answering your question, is what do we use for water demands? And that is definitely based on data sets that are available there. So, but that's not necessarily local data, is it?
No, it's what we do is, because these are global studies, we use reported data from FAO, which are usually on like Aquastat. We also use data on, so that's for the current water use. And we downscale them based on population densities, and also based on the locations where the industry is, and we also know what the agricultural or the land use is. So we know also where the irrigation is taking place. So based on that, we calculate water demands per sector, and these are then resolved by the model. But these are global sets. So for the future, we sort of have to model what will happen to the water demand, and that is the most difficult part, to be honest. Yeah.
But just to add on that, we do use local data to validate our models. So I simulate water declines, and I validate it, for example, with Central Valley data or data from the High Plains.
Yeah.
I think we have a question on the chat.
We have a question from Irene Klotz from Discovery Seeker. Irene asks, could you please describe the data you used for the study?
So that's the same question.
Well, maybe you can start with the hydrogeology, so the subsurface. How did you reconstruct
Yeah, so
it?
that's a good start, because that's actually one of the new things about this study. So how did we parameterize the aquifers? And so we used two data sets, global data sets again, one on lithology and one on permeability. And that's, well, defining how permeable our aquifers are.
Yeah. So you have to understand there's actually three ways around now to do this stuff. First is, I think you probably know most about, that's using GRACE data. That's the gravity satellite. That gives you low resolved but observed changes in gravity signal, which you then have to disentangle in the part that is groundwater, and there's modeling in that too. Then there's studies that we did as a group before, where we looked at, we estimated water demand and therefore water abstraction and recharge from a global hydrological model, and the difference between the two is then the depletion, but that's depletion in cubic meters or in millimeters, but it doesn't take account of the fact that there's surface water groundwater interaction. And what Inge did in their model is that whenever you start pumping groundwater and you start lowering the groundwater table, you get additional recharge from the surface water. So that partly counteracts the depletion. And that is in this model, and that is, I think, also one of the new parts.
Is there another question from the chat?
We have another two questions from Irene. The first, she asks that you please address reduction of groundwater with respect to sea level rise due to glacial melt.
Yeah? Okay, so I think she means what is the contribution to sea level rise of groundwater depletion. There is a notable contribution, which we estimated from all the studies, not from this one, to be between, say, 10 and 20% of the current sea level rise is attributable to water taken from aquifers. So that's sort of the ballpark figure you have to think about.
Second question, about how much water is in the ground worldwide?
So that's a good question because actually we don't know how much water there is. Because there's no global data about how thick are the aquifers and how much water can they hold. So that's one of the big unknowns. But with studies like this, we can at least estimate how much water there is. And also, I think it's not the question how much water in total is there, but how much water is there available. So that's also why we are looking at these limits. So how much water is there available until 100 meter or until rivers will run dry? I think that are the questions we try to answer.
Marc at Scientific American. I missed the first 2 minutes, so I apologize if you brought this up. But your last slide talked about limits in terms of economic limits, and that your unit was 100 meters, I believe. It sounds like the old arguments about oil, that we're running out of oil, and really not running out of economically recoverable oil. Could you talk about how much of a consideration that is, and why your limit is what it is?
Yeah, so that's also a good question. And maybe it's a little bit hard to answer because it's, yeah, so I took just 100 meter and it's based on other studies, but it's still like, so 100 meter in India and say like, okay, the wells dry up in India, it's something different than 100 meter in the U.S. So it's also a thing that I should still play a little bit with. So it's not a hard level to say like it's 100 meter.
Now we use two levels, 100 and 300, basically. The 100, you should first of all notice that it's not necessarily the depth of the well, but it is the depth that the water is in the well, right? So you can actually drill a well to 1,000 meter deep, but as long as the water rises within 100 meters of the surface within that well, you can get it up with a regular submerged pump. So until 10 meters, you can actually push it up. You can use or you can pull it up with a hand pump. Until 100, you have to push it up with a diesel or electric pump that is submerged. But if you go to greater depths, you need industrial pumps to do that. And a regular farmer in India is not able to afford that. In the U.S., they do. And in Great Plains and in California, they go deeper. But if you go deeper than 300 meters, there's sort of a rule of thumb. We got this information from people from World Bank. Then basically you go from a €100,000 well that is an industrial well to a few $1 million well that is used in the oil industry. And then you might as well start desalination plants because it's too expensive to pump it up from deeper down. So that's the sort of what we see as the technical limit for water use, even for countries as the US and Saudi Arabia, for instance.
Are there any other questions?
Bas den Hond, Trouw Daily Newspaper, the Netherlands. Same apologies for me, I missed the first minute or two. But you use models out to 2100. I'm assuming those include climate change and different patterns of rainfall and amounts of rainfall. Climate is supposed to be hotter and wetter, but not everywhere. Are we? Is that improving the situation, or are we out of luck and does it rainfall where it doesn't get into groundwater anyway?
That's a good question. And
how certain are we about those things?
Sorry, say again?
And how certain are we about those things?
Well, I'm not super certain. So the question was, so looking at climate change, is it going to change for which regions is worse or not? So we definitely see in the climate signal that for the regions where we expect drier situations and where the demands will increase, so there's less surface water available, so more groundwater abstraction, more depletion. But for example, in the climate models, they simulate more rainfall in India, so we see a decline in the well, not really a decline, but it's less steep. How do you say that? So
tapering off.
Yeah. So that's what we see in the future.
So and this is also to add to that. The uncertainty about climate change, or what we typically do, because this is just still work in progress, because Inge will redo this with a number of climate models. She now run with one climate projection, but will take 4 or 5 to get, say, the uncertainty in. And if you take then the average of that, you get what they call an ensemble mean that gives you sort of the expected value of the future given the uncertainty in the climate.
Yeah.
Are there any other questions in the room? Are there any other questions on the chat?
None here.
Okay, thank you very much. That concludes our press conference.
That gentleman.
Oh, are you a reporter?
Can I ask a question?
Sure.
Hi, I'm Maury Roos, an individual from California, and I'm wondering, for all these areas of groundwater or serious groundwater overdraft, if you stop that completely, how much of an effect, what percentage would it be on the agricultural food production for the world?
So if we totally stop abstracting groundwater, what is the effect?
Well, I can answer that, I think. There's the
Yeah.
numbers. About 17 to 18%, 1718, of the area globally is irrigated, but it's responsible for 40% of the food production. And so 40% of the food production comes from irrigation, and half of that is irrigated with groundwater. So you're talking about 20% of the food production that would be affected if you would stop using groundwater for food production. If you would stop the the groundwater that is non-renewable, then you talk about 5 or 6% of the food production is affected. Yeah.
Okay, thank you. There are no more questions. That concludes our media Q&A. Thank you very much.
Okay.
And next up, first results from Axial Seamount, an active underwater volcano, coming up at 9.